Hello dear students, I Abhinav Negi welcome you all in this faculty driven platform that is Resultant. I hope you all are doing fantastic guys, and in this session we will be doing some short tricks of shear force diagram and bending moment diagram, how to draw the SFD and BMD of a problem, how much tough it is just in 2 minutes or even less than 2 minutes. Maybe it's the toughest problem of the book, but we can do it very fast from this method. Not only that trick guys, but we will be learning that what actually is shear force here, what actually is bending moment, how it is useful, what is significance, what is the visualization of SFD BMD. That we will be doing in this session guys. Okay, so quickly like and share the session with all, so all the students, your friends can be benefited. Guys, please let me know audio video is fine. Tell me guys, audio video is perfectly fine. Please let me know. Okay. Audio video is fine. Let me check it. Okay. Okay guys. So guys, this is about me. Those who are new in the channel, let me introduce myself. My name is Abhinav Negi. I have done my MTech from IIT Delhi. Got all India rank 164 in 2012. You have to score a better rank than this. This is my Telegram group. You can join me here in Civil by Abhinav sir. Already guys, more than 6,000 students have joined here. You can also join me there. Okay. So what is SFD BMD? What is shear force diagram, bending moment diagram? What is its significance? That we will be going to study in this topic, and then later on we'll be doing that how the SFD BMD can be drawn very fast. Okay, so quickly tell me on the comment guys, quickly tell me on the comment box. Ready guys, everyone ready guys? Come on. Okay guys, so let's move further guys. Suppose this is a beam, okay, and in this beam any force may be acting. Okay, these force may be vertical, these force may be in any other direction, maybe horizontal, maybe vertical, maybe inclined, any direction the force is acting on this beam. Okay, now guys, inclined upward, let me take it, the cross section of the beam is xx, yy and zz. This is the xx and yy section, this is the zz axis. Okay, so let me take the cross section as yy, xx and zz. Now let me tell you guys, the axes which are passing from the plane, like this, these are called as transverse axis. And the axis which is perpendicular to that cross section, let this be the cross section, the axis which is perpendicular to that is zz, that is called as longitudinal axis. Okay, so xx and yy are the transverse axis and zz is the longitudinal axis. Now guys, in this beam, now let I cut a cross section from here. After cutting it from here guys, if I cut it from here guys, now the force on the one hand side will be looking like something like this. Okay, let me take it that here one more force is acting like this. So on the left hand side of this xx cross section, how many forces are coming? 1, 2, 3, 4. 1, 2, 3, 4. So if I see only this one part, how this one part will be looking? So one part will be looking like this. I have made it little bigger also. Zoom. Okay, let me tell you, from x-axis on the left hand side, these are the external force. Okay, this we are applying on this beam, or any column is applying, or somebody is applying on this beam. These are the external forces. Now from x-axis left hand side, if I see 1, 2, 3, 4 forces, so this will be looking like this. 1, 2, 3, 4. This is the x-axis axis now. Okay. Now guys, if the whole beam was in equilibrium, this whole beam was in equilibrium, suppose there are some supports or whatever, then this small part 1 may be also in equilibrium. Na? If this whole beam is in equilibrium, then small part is also in equilibrium. Now guys, if I am in equilibrium, my nose is also in equilibrium. Na? Okay. So guys, now this one part is also in equilibrium. Now again I take these are the axis, xx and yy are the transverse axis, and zz is the longitudinal axis. Now guys, if this whole part is in equilibrium, or if this whole beam was in equilibrium, so this small part is also in equilibrium. Now in this small part, to be in equilibrium, guys, some forces and movements will be coming. Okay, some forces and movements will be coming. Like, first of all, if in x direction there is net force, whatever it is, if in x direction there is net force, whatever it is, suppose 32 newtons, then in opposite direction from here, xx force should be coming, na? Then opposite direction, this sx force should be coming, na? Okay, let me make it with blue color. Yellow color is the external forces. Okay, so guys, from here in x direction, suppose 32 newton or whatever alpha newton is coming. So for balancing in opposite direction, there is a sx force coming, na, in opposite direction. Okay, to balance it in opposite direction, this sx force is coming. Yes sir. Okay, suppose in x direction, due to these forces or any other couple, mx movement is coming. So in opposite direction, mx movement will be coming here for balancing. Similarly, in y direction, there is net force. Suppose it is 42 newtons. Okay, so in opposite, in y, like this, sy will be coming. This sy will be whatever the force in the y direction, might be 42 newton or whatever. In opposite direction, it should be coming. If in y direction upward force is coming, then here downward force should be coming for balancing it. Similarly, in y, about y axis, there is some movement. So my movement will be coming for resisting it. Similarly, in z axis, there is some force. If it is, then in z direction there will be some force sz for balancing it. Suppose sz is coming here, so here sz will be coming here for balancing it, and mz movement is coming. So that means in the most general case of loading, when the forces are coming in any direction, movements are coming in any direction, inclined, x direction, y direction, z direction, any direction, the forces are coming on an equilibrium beam. Then when we cut one part of the beam, then guys, 6 internal things or internal forces will be coming, out of which 3 are forces, okay, in x, y and z direction, and 3 are movement in x, y and z direction. Okay, let me repeat again guys. When in a beam, in all general case of loading, means in the beam forces are coming like this also, 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 like this, and every direction force is coming, or maybe some movements are also coming. Then when we cut the part, then guys, to balance whatever the force in the x direction is coming, the opposite internal force as such should be coming. Whatever the force in y direction should be coming, in opposite direction sy should be coming, so that this whole part is equilibrium. Whatever the force in z direction should be coming, opposite sz should be coming. Similarly, all these forces or whatever the movements are, whatever those are conducting or whatever those are producing the movements about x, y and z, in opposite direction in opposite direction the movement should be coming. Now guys, before going further about what actually is shear force, what actually is bending moment, let me tell you one more thing. This is same like, suppose this is a bar. In this bar, this P and P force are coming. In this bar, this P and P force are coming. Now suppose I cut this part from the center. Take this x section. Now take this as one part, this as two part. Now guys, if I take this one part and two part, when I cut this from here, this whole bar was in equilibrium, na? Because summation, there is no force in x direction, there is no movement, there is no force in z direction, in y direction P and y direction downward P. So it is balanced, so it is equilibrium. So when I cut this and take this one part and two part, this should be also equilibrium, na? This one and two part should be in equilibrium, na? But in two part here only downward force P is acting. Therefore a P force internal should be acting here. Similarly in one part, only this external force P is acting for balancing. Therefore for balancing, in one part their downward force P is acting. This is internal force. This is internal force, that is of blue color. Actually here there is no force acting. Actually here there is no force acting externally. Once we cut the section, guys, then after cutting the section, for balancing this part, this P, here a P is coming for balancing this. Now it is in equilibrium. Similarly guys, for balancing this P is coming. So actually here there is no force. But once we cut this, then we get these forces. Internal force always equal in magnitude and opposite direction. One is P upward, one is P downward. One is P upward, one is downward. These are internal forces which comes after we cut the section. Which comes after we cut the section. These are internal forces. Similarly guys, in the same like here, you have understood very easily. Similarly guys, when here I cut the part, this is a beam. I cut it from here. See the left hand side part. Okay, I cut it here. Left hand side part was like this. Similarly for all these forces, Sx, Sy, Sz forces should be coming for balancing. Because here, in every direction loading is coming. Here also, here also, here also, here also. Maybe some movements are also coming. So guys, the three forces Sx, three forces, internal forces Sx, Sy and Sz should be coming for balancing the net force in x direction, net force in x direction, net force in y direction, net force in z direction. The forces should be coming. Now whatever these forces are producing the movement, or there are some other movements, for balancing them, the movements mx, my and mz should be coming for balancing. Now guys, if you closely look, what are out of Sx, Sy and Sz? Out of Sx, Sy and Sz. Out of Sx, Sy and Sz. What are the shear forces? Out of Sx, Sy and Sz. What are the shear forces? Like guys, here shear is tangential. Now this is a shear force on my cheek. This is tangential force on my cheek. This is a shear force. Now guys, see here, this x is tangential. Okay, this Sy is tangential on this plane. Sx is tangential on this plane. So these are the shear forces. This is actually what is shear force. This is tangential. This Sx is tangential on this plane. Sy is tangential on this plane. But Sz is not tangential. This is Sz. This is Sz. This is perpendicular. Okay, so Sz is actually the axial force. This is actually the axial force. So out of the three forces, two are shear force and one is axial force. Now guys, in your course, generally there is vertical loading. You have not seen like these kind of loadings. So in your course, generally this kind of shear force you deal, Sy shear force, because you deal mostly with vertical forces. So for vertical forces, this Sy should be coming like this. Similarly guys, the bending moment is coming here. The moments are coming here, mx, my, mz. Okay, the internal forces about the transverse forces. Okay, x and y are the transverse axis. About the transverse axis, the internal forces are the shear force, and about the longitudinal axis, the internal force is axial force. Similarly, about the transverse forces, this mx and my are bending moment. These are the bending moments. And about mz, see, this is the beam. This is the beam. Where is something that I can explain you? Okay, this is the beam about this axis. The moment is producing the torque na about the longitudinal axis. This is the bottle, and on this bottle, this pen is the longitudinal axis na. On this bottle, this pen is the longitudinal axis na. So about longitudinal axis, what is the moment? About longitudinal axis, what is the movement? It is torque. Thank you, Ashwar sir. Welcome. Okay, about the z-axis, this is torque, guys. So this is torque. Okay, so for the most general case of loading, we get 6 internal forces, out of which 3 are forces and 3 are moments. About the transverse axis, we get shear force. About the longitudinal axis, we get axial force. About the transverse axis, the movements are bending moment. They are bending it. Okay, these are bending. About y, it is bending it towards that side. About x, it is bending it top to bottom. But about z, that is not bending. That is torque, guys. So about transverse axis, it is bending moment, and here it is torque. Generally, in your case, it is vertical forces. So generally, you deal with this kind of shear force. Similarly, for vertical forces, guys, the bending moment is mx. Okay. For horizontal forces, guys, it will bend about this axis. That is bending moment about y. For horizontal, it will be bending it about this axis. But for vertical, it is mx. Okay. Okay, sir. Got it, sir. Okay, sir. Got it, sir. Now, this is what you learn in the college. What is shear force? Shear force is summation of transverse forces either to the left or the right. Suppose this is a beam. Suppose this is a beam. Now I cut it here. Okay, so what do you say? The shear force is the summation of force either to the left or to the right. Okay, now let me take a sign convention also, that from sections, if this is a section, the left hand side upward force is positive. Okay, and right hand side downward force is also positive. Whatever the section you are taking, left hand side upward or right hand side downward force is positive, and whatever the section you are taking, left hand side downward or right hand side upward is negative. This is the sign convention. You can take just reverse also. There is no principle or theorem here. Okay. Similarly, guys, if I take shear force at XX section, here I have taken. So shear force is the summation of left or right that you studied in the college. Na? So what is left? 2 downward. So left downward is negative. So -2. And left one is 4 upward. So left upward is positive. So -2 and +4. -2 and +4, that is 2. From right hand side also it will be same here. Right hand side, from right hand side, this is 10 downward. So right hand side downward is +10. And from right hand side, this is also 8 upward. So right hand side upward is minus. So +10 -8 is also 2. Both are same. Okay, now this is what you learn in the college, guys. But what actually is shear force? So what actually is shear force? Let me tell you. If I cut it here, if I cut it here, so from here this is 4, this is 2. Now, guys, if the whole beam is in equilibrium, if the whole beam is in equilibrium, let me consider the force equilibrium right now. So this small part is also in force equilibrium, na? This small part is also in force equilibrium, na? So 4 upward and 2 downward. So for making it 2 here is coming, na? That is the tangential to that section. That is the shear force. This 2 you are getting here as shear force. You can see from the right hand side also, yeah. You can see from the right hand side also. This actually is shear force. What actually is shear force? This is. From right hand side, this 10 downward is coming and 8 upward is coming. So for balancing this 10 downward and 8 upward, 2 upward should be coming, na? So this 2 upward which is coming, actually here there is no 2 acting, na? Actually here, this is no 2 acting, na? Actually here there is no force acting. These are the internal forces which we get after cutting the section. So after cutting the section here, 10 downward and 8 upward. 10 downward and 8 upward. Since whole beam is in force equilibrium, therefore small part is also in force equilibrium. So 10 downward, 8 upward, so 2 upward should be coming for balancing it. 2 upward should be coming for balancing it. That is the shear force, guys, tangential to that section. And internal force are always equal in magnitude. 2 and 2, both are 2 and 2. Okay, but from one side it is in one direction, from other side it is opposite direction. Like I just told here, na, come on. Internal force are always equal in magnitude, P and P, and opposite in direction, guys. Okay, got it? Yes or no? Everyone, please tell me on the comment box, guys. Are you getting this or not? Are you getting this or not, guys? Please tell me. Please tell me, friends. Everyone. Everyone. Any doubt? Any doubt? Any doubt? No? Okay. Okay, thank you, sir. Now, guys, if I talk about the movement, bending movement, there are 3 sign conventions. From everything it is coming same. First of all, where is bending movement? Come on. Here, bending movement is, it is a summation movement either from the left or right. Okay, suppose this is a thing. This is a beam. 4 upward, 4 downward, exactly at the center. So it will be 2 and 2 for a simply supported case. Okay. Now if I cut a section there, this is a beam, I cut a section here. This is a beam, I cut a section here, guys. Okay. Now once I cut a section here, I want, guys, what will be the shear force here? What will be the shear force at XX? Shear force is summation of force either to the left or to the right. Let me see from the left. So left, what is the sign convention? Left upward is positive. This was the sign convention. Left upward is positive. And sections, this was the sign convention. So shear force at XX from left hand side is upward 2. So this is 2. Or from right hand side also, yeah, right hand side downward is my plus. Section right hand side downward is plus. And this is 2. Section right hand side upward is This is sections right hand side. Upward is minus. So this is also 2. Both are same. Now what is the significance of this? What is 2? So what is 2? So 2 is once we cut a section here, at one part if I cut a section here, this is 2. Considering only force equilibrium, this shear force 2 should be coming now. So this is actually this coming. This whatever the shear force is now, which is coming here, this is actually this. And the representation of this shear force at every section here, representation of this shear force in all these sections. Representation of shear force in all these sections is shear force diagram. So what shear force diagram represents? Shear force value at each and every section. Now what is bending moment? Bending moment is summation movement either from the left or right. Okay, so let this be 2 meter or let this be 2 meter. Okay sir, let this be also 2 meter. Let this be 1 meter sir. Let this be 1 meter sir. 1 sir, 1. So what is bending moment? Bending moment is summation movement either from the left or right. So let me first of all find from the left. So what is the movement? What is the movement? Summation of movement either from the left or right. I am saying from left. 2 into 1. But positive or negative? So for this we have some sign convention. First, simple sign convention. That upward loading, if it is na, you have taken the load, you have taken the movement due to load. So if it is upward loading either from the left or from the right, it is always positive. Okay, so this is upward load. One was 2 into 1. Okay, 2 into 1. 2 is upward load, so it is positive. Okay, let's see from right hand side also. This 4 downward load either from left or right. Downward load cause negative bending moment. So 4 is downward minus 4 into what is this? This distance is 2. This distance is 1. So this is 1, and this is upward. Upward is positive. Okay, positive 2 into what is the distance? 2 plus 1, 3. From here to here 2, here to here 1, 3. So minus 4 plus 6 is again plus 2. Okay sir, this is one sign convention. I want to tell you other sign convention also. Sir, this you told us sign convention. What is this? Section left hand side clockwise movement is plus. Let me draw it here. Section left hand side clockwise or right hand side anti-clockwise is plus. Section left hand side anti-clockwise or right hand side clockwise is taken as minus. So this is sections left hand side 2, and 2 into 1 is a clockwise, so positive. This is section right hand side 4 into 1, it is also clockwise. 4 into 1, it is clockwise. So section right hand side clockwise, is minus, and this is 2 sections right hand side like anti-clockwise. 2 into 3 is anti-clockwise. Sections right hand side anti-clockwise is plus, so plus. Okay, this is all from all sign conventions. Answer will be coming same. So now one is sagging and hogging. If any part is making, if any force or movement is making beam like this is sagging. If any part or any force or movement is making the beam like this is hogging. But this is totally rubbish, guys. This sagging and hogging is totally rubbish, because if you call this sagging for this person, this becomes hogging. The same portion for this is sagging, for same curvature for this is hogging. Now you say, sir, why the person will be reversed? Okay, let it be frame case. If this is becoming like this, for this person it will be sagging, but for this person this will be hogging. Okay, so sagging, hogging always depends on frame of reference. Actually, sagging, hogging is rubbish. For a civil engineer, it is more important where to put reinforcement. Okay, since concrete, not concrete, guys, any brittle material, whether it is concrete, cast iron, anything, is weak in tension. So where the tension is coming, there we have to put the reinforcement. So actually, sagging, hogging is nothing to do. Actual thing is where to put the reinforcement. Okay, okay, ECG sir. So here, this 2 is actually, if we lock the beam here, this 2 is actually making the beam like this, sagging. So it is positive. This 4, if we lock it here, this 4 is making the beam like this. So that is hogging, so minus. This 2 is making, if I lock it here, 2 is making the beam like this. So 2 is sagging. Okay. So what is the bending moment coming? 2. From here also 2, here also 2. 2. So bending moment is 2. But sir, what actually is bending moment? Like you told us, what actually is shear force? Please sir, tell us what actually is bending moment. Sir, please tell us what actually is bending moment. Okay, cut a section. This is one. See the one part. From 2 also it will come same. If you cut this 2 part like earlier, it will be same. Okay, this is 2 meter. This is 1. Now if I make the free body diagram for making it in equilibrium, because whole beam is in equilibrium, the small part is also in equilibrium. If whole beam is in equilibrium, small part is also in equilibrium. So for 2 upward, 2 downward will be coming. Actually, this is shear force, because in this section this is tangential. In this section this is tangential, it is shear force. But still it is not in equilibrium, yaar. If this is 2, this is 2, yes, it is in force it is equilibrium, but it will rotate like this, na? It will rotate like this. So internal movement will also be coming. 2 into 1 is producing and clockwise movement. So here 2 into 1 anti-clockwise movement should be coming. And that is the bending moment that we are getting. That means if we cut the section here, we will be getting shear force 2 and bending moment 2. Give me yes or no. Give me yes or no, please. Give me yes or no, please. Everyone on the comment section, guys. Everyone on the comment section. Got it? Great. This is the bending moment. Now guys, these all things are the feeling what actually is shear force. What actually is bending moment? What actually is shear force? What actually is bending moment? Okay? What actually is shear force? What actually is bending moment? But now if you want to do it very quickly, draw the shear force diagram very fast. We want to draw the shear force diagram very fast. Then hire some AN technique, Abhinav Negi method. Although that is not my method. Okay, just I am saying the name. What is that? You just remember few points. What are those few points? First point, whenever there is upward loading, shear force will jump. Whenever there is upward point load, shear force will jump. Whenever there is downward point load, shear force will fall. Whenever there is upward point load, shear force will jump. Whenever there is a downward point load, shear force will fall. How to use this, I'll tell you. Don't worry about that. Now, whenever there is a clockwise movement, bending moment diagram will jump. Okay. And whenever there is an anti-clockwise movement, bending moment diagram will fall. Just remember this. We will make each and every question very fast, guys. Okay, we'll do each and every question very fast. Just remember these few things. Okay. Now, whenever slope of bend, this we can, guys, all these points are not tricks. We can derive these each and every point. Okay. Slope of bending moment diagram is shear force. From V, I will represent shear force. V, I will represent it as shear force. V, I will represent as shear force. Okay. So slope of bending moment is shear force. And the slope of shear force diagram, dV by dx, slope of shear force diagram is load intensity. And guys, upward loading, whatever the method, AN method I am telling you, upward loading I am taking as positive. Okay, and downward loading I am taking as negative. Upward loading I will be taking as positive, downward loading I will be taking as negative, guys. Any doubt? Upward loading positive, downward loading I will be taking as negative. Now it is visible. Guys. Okay, some autofocus is there. Upward loading positive, downward loading is negative, and I will be making the beam. Okay, direction drawing will be left to right. I will make from left, I will go to right. Okay, from left I will go to right. Okay, from left I will go to right. Okay. Okay. Now, from all these points, now I can draw SFD BMD very fast, guys. Okay. Yes, I know that will be automatically corrected. Don't worry about that. Okay, whatever drawings I'll be making from left to right. Okay guys, all these points you can draw SFD BMD very fast, all these points and some slopes. Okay, like I'll be taking this as graph 1, graph 2, graph 3, graph 4, graph 5, graph 6. Graph 1 is slope is, what is slope? Angle from x-axis na. So from here, from angle axis is acute angle. Angle from x-axis is acute angle. Tan 30, tan 40, all these values are positive. Okay, and it is constant, all angles are constant. Now here the angles are decreasing, so it is positive, acute angle is positive, slope is positive, but slope is decreasing. Here slope is acute angle, so tan 30, tan 50, all these values are positive, but it is increasing. Similarly guys, here the slope is obtuse angle, tan 120, tan 130, tan 140, all these values are negative, but it is constant. Similarly here negative, and magnitude wise decreasing. Magnitude wise decreasing means here you take the slope, here it is suppose 120 degree. So here you take slope, here it is suppose it is 150 degree. So magnitude wise you will see the magnitude wise it is decreasing, not sign wise, magnitude wise. Similarly this is negative slope, magnitude wise you can check it will be increasing. Magnitude wise you can check it will be increasing. Okay. Okay guys, everyone. Okay, so these graphs are there and these values, now you can draw any question in 2 seconds. Ready guys? Ready guys? Suppose this is a beam and in this beam the 4 kN node is coming exactly at the center. Exactly at the center C point 4 kN load is coming. So here 2 kN upward, 2 kN upward in a simply supported beam. Now you take, I want to draw SFD. While drawing SFD, you have to see the loading diagram. So what I told you, upward load, point load, shear force jumps na. I told you na, upward point load, shear force jumps, upward point load, shear force jumps. So here there is upward point load 2 kN, shear force jumps, upward point load, shear force jumps, upward point load, shear force jumps, upward point load, shear force jumps. Then after that what I told you, that shear force slope is load intensity. Shear force slope is load intensity. From A to C there is no load. From A to C there is no load. From A to C there is no load. So load intensity is 0. If load intensity is 0, that means the shear force will be a straight line. Straight line, slope will be 0. Then upward point load, shear force jumps na. I told you upward point load, shear force jumps na. Upward point load, shear force jumps. So downward point load, shear force fall. So from +2 falling to 4. Downward point load, shear force fall, it reaches to -2. Okay, then again C2B no load. C2B no load. If no load, then shear force slope is 0. Slope is 0 means straight line. Okay sir. And after that again upward point load, shear force jumps. SFD over guys. Now what is the meaning of this SFD? What is this? Is two value. What is this? That if we cut a section here we get two internal force, cut an internal section here we get 2 internal force. Now bending moment. Guys, what is the bending moment slope? dm by dx. What is the slope of bending moment? What is the slope of bending moment? Shear force na. So from A to C, shear force is positive and constant. From A to C, shear force is positive constant. So bending moment slope is positive constant graph number. Positive constant graph number 1. So draw the graph number 1 here. Like this. Then C2B, bending moment slope is shear force, shear force negative constant, it is constant na, 2, -2. So bending moment slope is negative constant, slope negative constant, graph number 4. So slope negative constant, graph number 4 is like this, this is BMD. Now what is the significance of this BMD? Suppose here is this alpha value. That means if we cut it here, when you cut, we get the forces and internal movement na, internal force and internal movement. So when we cut here, you get alpha. Suppose here the value is beta. That means if we cut here, the internal movement for balancing that part, either this part or this part, will be beta value. Okay. Yes, Vinitsha. Okay, got it, guys. Everyone, please let me know. Let me do some more points. Some more questions. Suppose now it is a UDL. In simply supported beam there is a UDL. Now I want to draw SFD. While drawing SFD you have to see loading diagram. So upward point load, this is W na, suppose L length. So here it is WL by 2, here it is WL by 2. In 1 meter W load. So in L length, suppose this beam is of length L. So in L length there will be WL load and is symmetrical. So WL by 2, WL by 2. So upward point load shear force jumps here. Upward point load shear force jumps here. Upward point load shear force jumps here. Upward point load shear force jump, downward point load shear force fall. Upward point load shear force jump, downward point load shear force fall. So upward point load shear force jumps by WL by 2. Shear force jumps by WL by 2. Now after that, dV by dx is W. Okay. Now W is the shear force slope is load intensity. Load intensity downward. So downward what I told you? Downward what I told you? Negative. Downward is negative. Downward is negative. It is downward point load. So negative and constant. Because it's constant, na? UDL uniform. It is constant. So shear force slope is load intensity. Load intensity is negative constant. So slope of the graph, whatever I am making the graph of V now, whatever the graph of shear force I am making now, it is negative and constant. So negative and constant graph number, negative and constant graph number, negative and constant graph number, negative and constant graph number 4. Okay. So from here, graph number 4 like this. Then there is a upward point load. Upward point load shear force jumps, upward point load shear force jumps, SFD. Now to draw BMD, like drawing SFD we have to see loading diagram. Now drawing BMD we have to see SFD. Now bending moment slope is shear force. Bending moment slope is shear force. Bending moment slope is shear force. Shear force from A to, let this point be O. From A to O, shear force positive and magnitude wise decreasing na yaar. Left to right we have to go. Decrease. Okay. So bending moment slope is shear force. Shear force is positive decreasing. Shear force is positive decreasing. Shear force is positive and decreasing. Okay. So positive and decreasing graph number, positive and decreasing graph number 2. Okay. So it is graph number 2 from there to there. Now after O, okay, O to B, shear force is negative and magnitude wise, see the magnitude wise, only magnitude, more, increasing. So after O to B, shear force is negative and increasing. So bending moment slope is negative increasing graph number, negative increasing graph number, negative and increasing graph number 6, negative increasing graph number 6. So graph number 6 is like this. Understood? Understood? Yes, it is, sir. Welcome. It is, sir. Welcome. Okay. Got it, guys? Everyone? Got it? So here it is positive and decreasing, then it is negative and decreasing. Now let us do one more question. Okay, hit this question hard. Okay, oh. Okay, here is the point reaction RB and here the reaction RA. Now I want to draw the shear force diagram. For drawing shear force diagram, I have to see loading diagram. Whenever there is upward point load, shear force jumps. Jump. Upward point load, shear force jumps na. Thank you, sir. Upward point load, shear force jumps na. Upward point load RA, shear force jumps. Upward point load RA, shear force jumps. Upward point load RA, upward point load, shear force jumps na yaar. Upward point load, shear force jumps na yaar. Upward point load, shear force jumps na yaar. So upward point load RA, shear force jumps. So point load is RA, shear force jumps by RA. Now shear force slope is load intensity. Shear force slope is load intensity and load intensity is downward. Downward means negative and magnitude wise increasing na. Negative and magnitude wise increasing na. It is downward, so negative and magnitude wise increasing. See left to right, more, increase. Okay, so shear force slope is load intensity. Load intensity is negative and increasing. Downward load is negative and increasing. Okay, negative increasing graph number, negative increasing graph number 6. Negative increasing graph number 6. So shear force will be like this graph, toing. So So like this graph, like this graph, like this graph, twing. Then upward point load RB, upward point load shear force jumps, upward point load shear force jumps, upward point load shear force jumps. Got it or not? Now while drawing bending moment diagram, we have to see SFD. While drawing bending moment diagram, we have to see SFD. So bending moment slope is shear force. Bending moment slope is shear force. Bending moment slope is shear force. Now let this point be A. So A to O, shear force is positive but decreasing. Shear force is positive, V is positive and decreasing, magnitude wise decreasing. Like see here, this value lesser, positive but decreasing, positive decreasing. So bending moment slope is shear force is positive decreasing, A to O positive decreasing, A to O positive decreasing, positive decreasing graph number, positive decreasing graph number 2, 2 like this, 2 like this, 2 like this. Okay, so positive decreasing graph number like this. So 2 like this. Now O to B, shear force negative and magnitude wise increasing. Magnitude wise -5 is bigger than -2. Magnitude wise, it is negative after O point. O to B it is negative but increasing. More. Negative and increasing. Negative increasing graph number. Negative and increasing graph number 6. Negative increasing graph number 6 like this, 2e. Okay, so negative increasing graph number like this, this is BMD. Now guys, there is lot of thing in SFD BMD. Like we can, from AN method we can find out the values also from this same concept. Now how to find that dm is equal to v dx. Now integrate this from 1 to 2. So m2 minus m1 is equal to area under SFD. Okay, m2, like let this be point m2, m1 is 0, so m2 minus 0 is area under this curve. Like this we can find the points also. There are various things there, inflection, conflection. If there is a symmetric beam, symmetric in supports and loadings, SFD will be anti-symmetrical, BMD will be symmetrical. Okay, like this is symmetrical, like this is symmetrical. So SFD is anti-symmetrical, plus minus, BMD is symmetrical. Like again, this is a symmetrical beam. Symmetrical should be loading and support. Okay, kahan gaya? This is symmetrical, SFD anti-symmetrical, BMD symmetrical. Okay. Okay. So guys, later on, I hope you enjoyed this method. Okay. Now guys, this is our number, support@resultant.in. You can connect us. This is our number. You can connect our WhatsApp here, or you can connect me here. Personally, you can connect me here. And this is my mail ID, Abhinav@resultant.in. At present, there are no batches. Our admissions are closed after 2nd May. Okay, but in June we will open and we will announce when it will be there. We will announce that as well. Okay. Thank you guys. See you in the next session. Take care guys, and like and share the video. And if you want, you can subscribe the channel as well. Thank you guys. Take care.